direct, analytical system. We tend to conceptualize artificial intelligence as a synthetic mind. In reality, modern computational systems parse the chaos of the physical world by forcing it into rigid mathematical structures. To understand this, we have to separate science fiction from software engineering. The sci-fi concept is artificial general intelligence, or AGI. AGI is a hypothetical system possessing broad, transferable cognitive reasoning across multiple domains. What we actually build today is artificial narrow intelligence, or ANI. ANI consists of highly specialized, task-oriented algorithms programmed to achieve specific objectives. Modern narrow AI does not think. It executes massive operations using statistics, linear algebra, and calculus. It is an engine built purely for mathematical prediction. The engineering challenge is translating the messy, unpredictable variables of reality into a format these predictive algorithms can process. This architectural map illustrates the field's taxonomy, divided into 3 pillars: supervised, unsupervised, and reinforcement learning. While processing exabytes of data, they operate under a fragile constraint hovering above them: the human ethical frameworks of fairness, transparency, and accountability. The defining challenge of algorithm design is recognizing that mathematical optimization ruthlessly mirrors the bias and chaos of the real world. We begin with supervised learning. This sector of the map shows an architecture trained by feeding an algorithm massive datasets of explicitly labeled input-output pairs. The objective is strictly deterministic. The algorithm processes millions of examples to deduce the mathematical relationship mapping the independent variables to the human-provided label. A foundational classification algorithm in this space is k-nearest neighbors, or KNN. KNN is a non-parametric approach that classifies new, unlabeled data points based entirely on their mathematical proximity to existing labeled data. This animated scatterplot shows KNN in action. When a novel observation drops in, the algorithm calculates the Euclidean distance to the closest training points, its neighbors, and assigns the class label that represents the majority. This supervised paradigm scales up to tackle incredibly volatile problems, such as forecasting global stock market movements, as seen in this photographic ticker data. Traditional algorithms fail here. Financial time series data is nonlinear and non-stationary, meaning its statistical properties change over time, rendering it nearly identical to random white noise. To extract predictability from this chaos, engineers deployed deep learning architectures, specifically long short-term memory networks. LSTMs are specialized recurrent neural networks designed specifically to process and predict sequential data. LSTMs utilize internal memory cells and gating mechanisms. These mathematical gates allow the network to retain long-term macroeconomic dependencies, like inflation rates, while actively discarding irrelevant short-term daily price fluctuations. Supervised prediction handles high-dimensional sequential data with high accuracy, but it is bounded by a strict limitation. It requires humans to accurately and expensively label the past to predict the future. That reliance on manual labels introduces a massive enterprise problem. What happens when a dataset, like a global social media corpus, is too massive or expensive for humans to categorize? This central module illustrates unsupervised learning. Here, engineers unleash algorithms on raw, unlabeled data to autonomously discover intrinsic relationships and hidden structures without human guidance. The primary method for discovering these structures is k-means clustering. K-means is a centroid-based algorithm that mathematically segments data into distinct, non-overlapping subgroups based on inherent similarities. It operates on an expectation maximization loop. Expectation maximization is an iterative process where the algorithm drops random center points into the data, assigns nearby points to those centers, and continuously recalculates the mathematical mean until the clusters stabilize. However, modern unlabeled datasets, particularly text or high-resolution images, suffer from the curse of dimensionality. The curse of dimensionality occurs when the sheer volume of variables drives up computational costs so high that processing becomes mathematically intractable. To solve this, data scientists utilize singular value decomposition, or SVD. SVD is a linear algebra theorem used to compress massive matrices into a lower dimensional space while rigorously preserving their essential structural variants. This animated grid represents a commercial recommendation system, like Netflix. To solve the sparse matrix problem of millions of users interacting with a microscopic fraction of available films, Netflix adapted an SVD principle called matrix factorization, compressing the vast empty grid into smaller, dense submatrices. By mapping users and films to shared latent factors within this compressed mathematical space, the algorithm accurately predicts missing ratings without knowing anything about the actual content, genre, or cast of the films. Unsupervised learning forces order onto raw chaos, entirely without human intervention. It forms the invisible architectural backbone of the modern digital economy. Supervised and unsupervised models analyze static data, but operating in the physical world requires dynamic, sequential decision-making. This right-hand sector maps reinforcement learning. In this paradigm, an autonomous agent operates blindly within a defined environment. The system runs on a continuous feedback loop. The agent takes distinct actions that alter its state, and the environment returns a numerical reward or penalty based on that action. The mathematical engine driving this is often temporal difference learning. Temporal difference learning is an algorithm that iteratively updates a policy by balancing immediate rewards against the discounted predicted value of future states. This introduces the exploration-exploitation dilemma. Developers must actively program the agent to make random exploratory moves at a defined probability rate. Otherwise, the algorithm will get stuck exploiting early, suboptimal strategies instead of discovering the maximum possible reward. We see this abstract simulation applied to physical operations research, specifically within the multivariable chaos of urban traffic grants pictured here. Reinforcement learning agents evaluate real-time vehicle density and queue lengths from intersection sensors. They dynamically adjust the duration of traffic light phases, heavily outperforming the static timers used in traditional infrastructure. Global logistics firms like Amazon use deep reinforcement learning to solve the traveling salesperson problem for last-mile delivery. The traveling salesperson problem is a notoriously complex mathematical challenge to find the shortest possible route connecting multiple geographical nodes. By utilizing dynamic environmental feedback loops rather than static historical data, reinforcement learning bridges the gap between theoretical mathematical optimization and the unpredictable physical world. Despite their mathematical elegance, machine learning models possess no inherent morality, contextual understanding, or common sense. They optimize strictly for the parameters provided. When engineers deploy Blyblox algorithms trained on historically biased data, they guarantee the automated acceleration of societal flaws. Consider Amazon's experimental AI recruiting tool. The system was trained via supervised learning on 10 years of resumes submitted to the company, a male-dominated dataset. This animated diagram visualizes the mathematical consequence. The algorithm independently identified male dominance as a statistical factor for success. Consequently, the decision tree actively penalized female applicants, systematically downgrading resumes that included words associated with women's colleges or organizations. A similar failure occurred through adversarial manipulation with Microsoft's Tay chatbot. Tay was an experimental AI built on an adaptive reinforcement learning architecture meant to evolve its language patterns dynamically through public interaction. The deployment exposed a failure of symbiotic agency. Because developers failed to implement ethical boundaries, malicious actors bombarded the unmoderated system with toxic dialogue. The algorithm treated this as legitimate training input, optimizing into a racist engine within 24 hours. This enterprise crisis proves the garbage in, garbage out axiom. Algorithms function as mathematical mirrors, reflecting and scaling human prejudice. The long-term viability of machine learning requires more than raw computational advancement. Sustainable deployment depends on auditing and restraining these systems before they interact with the public. This requires explainable AI, or XAI, analytical frameworks designed to break open opaque black box models and isolate exactly which feature inputs drive a system's final decision. It also requires strict algorithmic hygiene.
Algorithmic hygiene is the mandatory practice of testing models in isolated digital twin environments to monitor for statistical drift and behavioral deviations before public release.
Machine learning architectures offer high-scale predictive utility, but their safety depends on ensuring the data they reflect is equitable